Knox Game Design. February 2022. 2D Collision.
Welcome everyone to Knox Game Design for February 2022. My name is Levi Smith. So this month I'm going to be talking about 2D collisions. Really haven't done a collision talk in the past. Been kind of putting it off because there is a lot of math involved. And with math being involved, I had to double and sometimes triple check some calculations to make sure that everything that I'm presenting is accurate. So first of all, we're just going to be talking about 2D collisions. May do a 3D collision talk later, but basically we're talking about collisions on a 2D plane, such as a monitor or computer screen. So the first, just to make sure we're all on the same page, the first collision we're going to talk about is the collision between 2 points. So a point just has an x and a y coordinate. So basically we're just going to check where x1 equals x2 and y1 equals y2, where the point is x1, y1, second point is x2, y2. So this may be useful for like grid style games like checkers or chess, where you got distinct, discrete rows and columns, where your y value will be your rows and your x values will be your columns. If you're not doing a discrete values, if you're doing a shooter or something like that, and using floats for your x and y value, non-discrete whole number values, then you'll probably want to add some tolerance in there. So if it's close enough and not an exact value match, but I'm not going to be talking about that in this talk. And also in this talk, I'll be using typical screen coordinates in a lot of game development environments and frameworks, where your x value goes from 0 to your screen width, from left to right, and your y value goes from 0 to screen height, going from top to bottom. And I also just want to say that everything that I'll be talking about can be used in any game development environment or framework. There are built-in functions to handle a lot of these, but the good thing about learning the basics, you can implement this yourself in whatever language or game development library as needed. So here it is, the 2 points, and to test whether they collide, basically, like I said, I got C# code up there that you could use for, say, Unity, where p1.x equals p2.x, and then we got the double ampersands for and, p1.y equals p2.y. So here's some examples. I mean, this is pretty common sense, but just to make sure we're all on the same page, in the top left corner, we got points 5, 2, and 1, 4. So 5 doesn't equal 1, and 2 doesn't equal 4, so they don't collide. To the right, upper right-hand corner, we got points 1, 4, and 5, 4. So the x's don't match, but the y's match. So they both have to match, so it doesn't collide. In the bottom left-hand corner, we got points 1, 2, and 1, 4. So the x coordinates match, but the y's don't match. So it's not a collision. But in the final one, we got 2 points, both 1, 4, and 1, 4. So both x and y match. So those 2 points collide. Okay, so here's the next step. A collision between a point and a line. So basically a line is defined by 2 points. Typically a line is infinite. It has a slope. But we're going to be talking about line segments, where a line has a distinct stopping point. So the line, as I mentioned, you got 2 points, both with an x and a y value. So to find the slope of that line, then what I learned in either high school or late middle school, like pre-algebra, it's called rise over run. So you take the differences between the 2 y values and divide by the difference between the 2 x values. And it doesn't matter which point you use. Either way you do it, the signs will all work out. So you'll get the correct slope value, whether you calculate it using the first point and then the second point, or second point and the first point. So what I learned in like pre-algebra or algebra, or maybe even geometry, is a line is defined by what we call slope-intercept form, which is y equals mx plus b. So y and x are any point along the line. M is your slope. Slope is basically just how steep the line is. So if you're going in positive x, y direction, that's a positive slope. If you're going the other way, it's negative slope. Then the b is the y-intercept. So what is the value of y when x equals 0? So one thing I mentioned on here is when you're calculating your slope value, watch out for integer rounding. If you're using a typed language, then sometimes when you divide by integers, it will usually round down unless you specifically cast those values when you divide as floats or doubles. I also mentioned that there are other notations for lines, but I'm just sticking with the y equals mx plus b. So to find the value for b, the y-intercept at 0, then what you do is you use basic algebra to put b equals, and then the y value for one of the points, and subtract off m times the x value from one of the points. So remember, we calculated m as the slope in the previous step using the rise over run. So that will give you the value of b. And as I mentioned, you can use either point for calculating that. So then to determine whether a point and a line collide, all you do is take the point that you want to test, then plug it into that y equals mx plus b. And if it's a valid statement, then you know they collide. Okay, so here's our line defined by 2 points and a point defined by x and y. Actually, should have just had x1, y1 for the point, but so here's the code in C#. Basically, we're calculating the slope, the m value, subtract the y of the first point or the second point, and subtract off the y of the first point, then divide by the x value of the second point minus the x value of the first point. And those are the two endpoints of the line segment. And then to calculate the b value, we just use the y equals mx plus b, but subtract off the mx right there from y, so we get b equals, and we take 1 point, the y value of 1 point on the line, then subtract off the slope times the x value. So that gives us our b value. So then to find whether the point collides or not, we just plug in the point value for y. If that equals the slope times then the point value for x plus b, then it collides. So here's a couple of examples right here. So we got a line defined by 2 points, 4, 5, and 6, 1. And then we got a point, 2, 3, x equals 2 and y equals 3. So to calculate the m value, basically we're going to subtract the two y values, 1 minus 5 divided by 2x values, 6 minus 4. So calculate that out, you get a slope of minus 2 or negative 2. Then to get b, we do y equals mx. So we're going to take that 6, 1 point. So we're going to do 1 minus, then take the slope, the m value, minus 2 times 6, which is the x value. And we do the calculation, that turns out to be 13. So the slope of this line, or the form of this line, is y equals minus 2x plus 13. So now that we have the equation for the line, then we can test any point that we want. So basically when we want to test this 2, 3, so we got plugging in the values for y and x, we've got 3 equals minus 2 times 2 plus 13, which is 3 equals minus 4 plus 13. So 3 equals 3 does not equal 9. So that means the point does not collide with the line. But in the second example, we're going to test a 0.53. So we're going to use the same line equation, y equals negative 2x plus 13. And we're just going to plug in 5 for the x value and 3 for the y value. So that gives us 3 equals minus 2 times 5 plus 13, which equals 3. 3 equals negative 10 plus 13, which gives us 3 equals 3. So that means it does collide with the line. So the next step is, which will probably be more beneficial in a game, is the collision between two lines. Typically, we probably don't want to do a point in a line. Like if we're tracing a bullet, then what we want to do is to test the collision from the previous point of the bullet to the next point of the bullet. Especially if the bullet's going very quickly, then we'll want to treat it basically as a line. So if you look this up online, you're going to find a lot of information about determinants, which is another way to do this. I kind of think of like, hey, if you're out in the woods and you're going down a path and there's a fork in the path, you can take one or the other, but you'll end up at the same location. So the method or the path that I'm taking with this is using the same y equals mx plus b form. You can calculate this by determinants, but I'm not going to go into that. So to determine whether two lines cross, basically you can use the same y equals mx plus b format for the line, and then basically you take the mx plus b for the first line and set that equal, or test equivalency to the mx plus b for the second line, because they both equal y. So if you assume they both equal the same y, then you can test whether they collide by testing that other portion, mx plus b. So basically we got m1, slope of the first line, x plus b1 equals m2, the slope of the second line, times x plus b2. So then you just solve for x, and to do that, you end up with, I'm not going to go into the math, it's just basically subtracting and dividing out those terms, but you end up with a value for x of negative b1 plus b2 divided by m1 minus m2. So that's the y-intercept, the difference between the two y-intercepts and the difference between the two slopes divided by the difference between two slopes. And that's probably essentially what the same thing that you're doing when you calculate the determinant anyway. Don't quote me on that, but I assume that's the same thing that's going on. And to determine whether that collides, we're basically going to check and see if the x value for the points on both segments fall between those values. So we're going to check if x is greater than or equal to the first line's minimum x. Then we'll check to see if x is less than the maximum x of the first line. Then check if x is greater than the minimum x of the second line, and check if x is less than the maximum x. So if we got two lines that go out into infinity, as long as those two lines aren't parallel, then they're going to cross somewhere. So when we calculate this x, basically we're calculating at what x value do these two lines cross. So we know they're going to cross somewhere as long as they're not parallel. So what this test here is doing is saying, hey, we know where the x value where the two lines cross. Is this x value a valid point on both of the line segments? So the difference between a line that goes out into infinity and a line segment is the line segment has a start and stop point. Okay, so here's the example. So we got two lines, both have 2 points, defined by x and y. Here's the calculations that I just did over here. So basically we're going to do the same finding of the slope, and the x value. your M1 and B1 and M2 and B2. So to find X, we're going to do minus B1 plus B2 divided by M1 minus M2. And then we're going to check and see if that X value is valid, a valid position on both of the line segments. So that's what these 4 checks here do. So here's a couple of examples. So we got first line segment goes from 4.5 to 6.1, and the second line segment goes from 2.3 to 3.4. So we're going to do the math, the y equals mx plus b, so we get m1 equals minus 2 for the first line, and b1 equals 13. I think that's actually the same line example in the previous example. And then for the second line, we get a slope of 1, and then the y-intercept, the b2 value of 1. So what we're going to do is calculate the value of x. So that's basically checking whether the value of x by plugging in those two values. So we get minus 13 plus 1 divided by minus 2 minus 1. That equals 4. So we know 4 is the x location where these two lines cross. So then we need to see if 4 is a valid x position on both lines. So we check on the first line, 4 is greater than 4 because the minimum x is 4 and the maximum x is 6. So 4 is between 4 and 6 inclusive. So then we check and see if 4 is on the second line. So the second line goes from x values 2 to x value 3. So 4 is greater than 3. So that means that 4, where the two lines cross, doesn't exist on this second line segment. So these two lines don't cross. So in the second example here below, we're going to use the same first line, 4.5 to 6.1. Then we're going to use, for the second line, 3.1 to 6.7. So the M and B for the first line are going to be the same. The M and B for the second line, we do the math, we get a slope of 2. And then for B, we get a slope of minus 5. And I also want to point out, if you're looking in like an algebra textbook, you'll find the y value, the y-axis going up instead of down. I'm just using down because that's typically how screen coordinates are laid out on a computer screen for games. So when you see a slope of 2, on here is going to be going down, down, and to the right. But if you look this up in a textbook where the y coordinates are going up, then a positive slope value will be going from right and up instead of right and down. Okay, so we got the M and B for both lines. So then basically we're just going to plug in that to calculate our values for x. So we get x equals 4.5. So that means that these two lines cross at 4.5. So to determine whether these two lines collide, then we basically plug that 4.5 back into our y equals mx plus b. Or basically, we take that 4.5 and determine if it's greater than or equal to the min x, and whether that 4.5 is less than or equal to the maximum x for both lines. So the first line goes from 4 to 6, so 4.5 is between 4 and 6. The second line goes from x value 3 to x value 6, so 4.5 is between 3 and 6, so that means the two line segments do cross. Okay, so now we're going to talk about points and rectangles. So this is another pretty simple one here. So we got a point with an x and a y value. We got a rectangle with an x and a y coordinate for the upper left-hand corner, and then a width and a height. And I'll just go ahead and say beforehand, some game programming libraries define a rectangle by 2 points. The upper left-hand corner and the lower right-hand corner. So basically, you just calculate the difference to get the rectangle's width and height. I think most libraries do define rectangles by the x and y and width and height, but if not, it's easy to convert that into width and height by using 2 points. So determine whether a point collides with the rectangle. We're basically just going to check and see if the point exists in the rectangle. So if the point x is greater than the rectangle x, and the point x is less than the rectangle's x plus the width, then we know the point resides within the rectangle, or it's between the rectangle's two x values. Then we're going to take the point's y value, check to see if it's greater than the rectangle's y, and check and see if it's less than the rectangle's y plus the height. So all 4 of these rules have to be true for it to collide. So here's an example right here, and yeah, it's just basically 4 checks anded together. And that's what it looks like in the C# code right there. So here's some examples. So the one in the upper left-hand corner, we got a rectangle defined by upper left-hand corner point of 2 and 1, has a width of 4 and height of 3. And then we're going to check and see if this point at 1, 3 is inside that rectangle. So the first test, we want to see if 1 is greater than the rectangle's x. So 1 is less than 2. So right off the bat, that rule is not validated, signified by that x right there. So we know the point does not exist in the rectangle. And then go ahead and do the rest of the check. So 1 is less than the rectangle's x plus width. The y for the point 3 is greater than the y value of the rectangle, which is 1, and 3 is less than the y value of the rectangle, which is 1, plus the rectangle's height, which is 3. So just being invalidated for that first rule determines that it didn't collide. So I put a note down here in the lower corner here. So the checks in X just signify whether it broke the rule. It does not signify, these are all valid statements. So it does not signify whether this is a valid statement or not. So in the upper right hand corner, we got a point 5, 3. We're going to check to see if that exists in the rectangle. So 5 is greater than 2, check. 5 is less than 2 plus 4, the x plus the width, check. The y value of the point is greater than the y value of the rectangle, so 3 is greater than 1, check. Then 3 is less than the y value of the rectangle plus the rectangle's height, which is 3 is less than 4, check. So that means the point exists within the rectangle. So then this lower left-hand corner, we got a 0.75. So in this one, 7 is greater than 2, so that validates that rule. 7 is greater than the rectangle's x plus width, so that rule, it invalidates that rule. It doesn't meet the requirements. It should be less. So that's an x. Then the y value, so 5 is greater than the y value of the rectangle, so 5 is greater than 1, check. But 5 is greater than the y value of the rectangle plus the rectangle's height, so that's an x. So it's to the right of the rectangle and below. So 2 of those rules are broken, which means it doesn't exist within the rectangle. So I'm not going to go into the collision, I didn't add it to this presentation, between a line and a rectangle. I'll just say I think the way to do that is to check and see if the line collides with each line segment of the rectangle, so at the top and the bottom and the left and the right of the rectangle. And then I think you have to do an additional check to make sure that the complete line segment doesn't lie within the rectangle. So that's just basically checking the 2 points of the line to determine if the line exists totally within the rectangle. And also talking about lines, one thing that I forgot to mention is you probably need to also add a check when you're calculating slopes to make sure the line isn't completely vertical. So if it's completely vertical, then your slope's going to be undefined. So You can set that undefined as a really large number, or you could write special code to handle that. And I think that's part of what the determinant does, is to check whether it's undefined or not. So anyway, I'm not getting into that. So here's the collision between two rectangles, and this is something very commonly used in games. So you got two sprites, and they're both represented by rectangles. You want to find if those two rectangles collide. And I'll just say, when I started developing games, I had some really hokey code for trying to determine the collision between two rectangles. So later on, years later, I found out there's a pretty easy way to calculate this. Instead of trying to figure out when the two rectangles collide, because I was like testing like the four corners of the first rectangle, determine if those are within the second rectangle, then determine if the first rectangle is within and around and all that. It's just a bad way to do it. So it's easier to check to see when the rectangles don't collide. So the first rectangle doesn't collide with the second rectangle if the first rectangle is completely to the left, completely to the right, completely above, or completely below. Then they don't collide. So then, to find out if they do collide, you just not that, Boolean not. And also mentioned here De Morgan's theorem, so you can basically have all these checks ANDed together, not to the left and not to the right, and not above and not below. So when I learned De Morgan's theorem, basically you can convert not A and not B to not open paren A or B. So you're flipping your ands to ors. And typically this is used for like circuit diagrams where you have gates, and so you don't have any OR gates, but you have AND gates. So you got not all these not ORs, so you can convert those to AND gates. I think you can also use it in programming to make your statement a little bit cleaner without all the nots. You can just have one not, then ORs for everything else. And I'll also mention, if anybody out there hasn't had geometry yet, a square is just basically a special instance of a rectangle. A square is a rectangle. It's just a rectangle where the width and height are equal. So if you've got squares, this applies to squares. Okay, so here's the code right here. So basically we're checking those four conditions to determine if the rectangle's to the left, to the right, above, or below, and doing the knots for all those and ANDing those together, or one knot and ORing all those together. Okay, so here's the examples that I came up with right here. So the first example, we got so the first rectangle is going to stay the same through all these examples. So we got a rectangle with an upper left-hand corner of 4, 1, x equals 4, y equals 1. The rectangle has a width of 4, and it has a height of 3. So now we have a second rectangle at position 1, 2 with a width of 1 and a height of 1, a square. So we're going to check each of those conditions. So we're going to check to see if the rectangle is completely left of the first rectangle. So 1 plus 1 is less than 4. So right off the bat, we know that these two rectangles don't collide because the second rectangle is completely to the left of the first rectangles. I have the other checks up there for the right, above, and below, but it doesn't matter. So unless they're all X, they don't collide. So in the second example, to the upper right-hand corner, so we got, in this example, the second rectangle completely surrounds the first rectangle. So we're going to check, is the second rectangle completely to the left? No, 3 plus 6 is greater than 4. Is it completely to the right? No, 3 is less than 4 plus 4. Is it completely above? No, 0 plus 5 is greater than 1. And is it completely below? No, 0 is less than 1 plus 3. So they do collide because none of those rules were validated. And by the way, the second rectangle is at position x equals 3, y 0 with a width of 6 and a height of 5. Completely surrounds the first rectangle, meaning that the two do collide. So in the third example, to the lower left-hand corner, we got the same first rectangle. The second rectangle is at position 1, 2, has a width of 5, and a height of 1. So as you can see, if you're watching the video, these two rectangles do collide. So it's from the first rectangle, it's colliding on the left side of the first rectangle. So we're going to check to see if it's completely to the left. No. Is it completely to the right? No. Is it completely above? No. Is it completely below? No. So since it's all no's, then it means they do collide. Okay, so here for the last example, we have a second rectangle with a position x equals 1, y equals 8, and with the 2 and a height of 1. So we're going to check the 4 rules. So basically the rules should be for the left, 1 plus 2 is less than 4. So it is to the left of the first rectangle. Then we check to see if 1, the x position, is greater than the x position plus width, the first rectangle. So it isn't to the right. It isn't above, but it is below. So 8, the y value 8 is greater than the y value of the rectangle, which is 1, plus the height of the rectangle, which is 3. So since 8 greater than 1 plus 3, then that's a check. So since there are check marks, since they're not all x, that means they don't collide. Kind of hard to wrap your mind around it, but basically just checking for all negative results. So if they're all negative, if all the conditions are not satisfied, then the two rectangles do collide. So kind of the last one that we're going to talk about here is two circles. So that's basically the 4 shapes we're going to talk about is points, lines, rectangles, and circles. So circles are actually really easy if you know a little bit of geometry. We go back to the old Pythagorean theorem. So Pythagorean theorem says that the distance between 2 points is a squared plus b squared equals c squared. Where your a is the difference between the two y's, and your b is the difference between the two x's, and the c is the hypotenuse. So to calculate c, basically you do a squared plus b squared, take the square root of that. And I'll go ahead and say up front, it doesn't matter whether or not the differences are positive or negative, because once they're squared, then they'll become positive. So you don't have to worry about taking the square root of a negative number there, since those two values are squared, which will always result in a positive value. So when I was originally creating these slides and examples, I was like, well, maybe I should take the absolute value of a squared plus the absolute value of b squared, but you don't even need to do that, because if it is a negative value, it will become positive because it is squared. Because a negative times a negative is a positive times a positive is positive. So really, you're calculating the hypotenuse, the distance between 2 points, or the hypotenuse of a triangle. So this is kind of weird, using a triangle to determine whether circles collide seems kind of doesn't seem intuitive there, but it does work. So basically, we're taking the centers. You got to know the centers of the two circles and the radius of the circle. So the radius is basically the distance between the center of the circle and the outside of the circle itself. Kind of think of it like as a pin and then a string attached to that pin, and then you draw all the way around. Or if you're using a compass, then the center is where the sticky point is, and then the radius is the distance between the sticky point and then where the pencil is. If people even use compasses anymore, then you use the pencil to draw the circle around the pointy part. Okay, so just trust me that you can use Pythagorean theorem to figure this out. So to find out whether the two circles collide, we're going to calculate the distance between the centers of the two circles, And if the distance between the two centers, as I have right here, is less than the sum of the two radius values, then the two circles collide. We've got a circle here and a circle here, and we're going to find the two radius values. So if the sum of those two radiuses is less than the distance between the two center points, then we know they don't collide. But if the distance between the 2 points, if the sum of the radiuses is greater than the distance between the two center points, then we know that they do collide. And I'll go ahead and mention I won't specifically have a slide for calculating whether a point, just a point, collides with the circle. But basically, you can determine whether a point collides with the circle by using a circle of radius 0 as your point. So it has an x and a y, and your radius would just be a 0 for a point. So all this applies to a point and a circle as well. And theoretically, you could determine if 2 points collide with each other by using the same process, just using radiuses of 0. But that's a little bit overkill. But theoretically, it still works. And oh, by the way, this doesn't work for ovals. So it's got to be a perfect circle. It can't be wide and skinny or anything like that. There's probably a way to calculate that, but I didn't look into it. Okay, so here's our two circles. They both have a center point. The first circle has a center point of C1x, C1y. The first circle has a radius of C1r. The second circle has a center point of C2x, C2y, and a radius of C2r. So here's our triangle right here. So we're going to take the difference between the two x values, two center point x values, and the difference between the two center point y values. We're going to square both of those individually, add those two together, and then take the square root. And oh, by the way, if you don't have a square root function in your favorite programming language, you can always set that to the power of 1 over 2 or 0.5. So use power 0.5 to get the square root. So if your C value, if the distance between those two center points is less than the sum of the two radius values, then they do collide. So here's an example in C# down here. So we're using the math f.power. So we're adding the two squares, then taking the square. I just went ahead and used power to the 0.5 f. And got the C value and check and see if that's less than some of the two radius values. So here's an example right here. So we got a circle, center point 2, 3 with a radius of 2. The second circle with center point 7, 4 with a radius of 1. So we calculate the A value. So the A's value is -1. The B value is -5. So that's the length of the two sides. And oh, by the way, it is a right triangle because it has a 90-degree angle where the A and B sides meet. So we got a -1 and a -5. So we square those. So we get 1 and 25. So that gives us 26. We take the square root of 26, and it approximately equals 5.01. So since 5.01 is greater than 2 plus 1, or 3, then that means these two circles don't collide. In the second example on the bottom, we got the same first circle, center point 2, 3 with a radius of 2, and our second circle has a center point 3, 4 with a radius of 1. So the A value is -1, the B value is also -1, so we square -1 plus the square of -1, which equals 2. Take the square root of that, equals approximately 1.41. So since 1.41 is less than the two radius values, 2 plus 1, 1.41 is less than 3. So that means the two circles do collide. Yeah, so that's basically it for all the basic shapes that I'm talking about. So I didn't do some like a line and a circle or a rectangle and a circle. I just wanted to keep this presentation simple. But there are libraries out there. So like in Game Maker, it uses place meeting along with some other functions. I put links here to references to these functions, collision functions, 2D collision functions. In Unity, you have on collision enter 2D, and in Godot, you use collision shapes, and there's a collide function. So I have links for all those on there. So I have a quick demo. So I was going to go back, and I got a lot of these already kind of queued up right here. So I wrote this little JavaScript applet, or I guess it's not an applet. This JavaScript app, web app. So basically, you can put in two objects. Yeah, so I got the 2 points right here. So I got the X along the top and the Y along the side right here. And I got basically 64 pixels to a unit. And a unit goes from 0 to 15 on the X and 0 to 10 on the Y. I mean, if I wanted to improve this, I could have it automatically calculate a scale or let you specify it. But basically, I got it down here, supported objects. So I got a point, a line, a rectangle, and a circle. So you specify points with X and Y. So we've got 1, 4, 5, 2. But we could change this to like 1, 4, 1, 2, and then press check collision. Then it's going to show where those 2 points are. Then right here it's just going to say not collided. In a future version, I'd like to have it where it actually shows you the calculations as well. So here's an example right here. And you can also specify this on the command line or the URL. You just do a question obj, then your first shape, then ampersand obj, then your second shape right there. So I thought this would be neat if you wanted to give an example to a friend or something. You could just put those values on the URL and share that URL right there. And by the way, this is on my website. I'll link to it on the Knox GameDesign.org website as well. So these are basically the same examples that I just went through earlier. So here's an example of first object is a line 4, 5 to 6, 1, and the point is 2, 3. So we got it right here. Here's our 2, 3 for the point, and the 4, 5 to 6, 1. So you can see these don't collide at all. But if you look at this one right here, this is the same example from the presentation slide. We've got 4, 5, 6, 1 and a point of 5, 3. So you can see it's right there on the line, and it does collide. So here's a line collision right here. So we got the same line, 4, 5 to 6, 1, but the second line is 2, 3 to 3, 4. So you can see these do not collide. And then here's 2 lines that do collide. Same first line. The second line is 3, 1 to 6, 7. It tells you right there they collided. So here's a point rectangle. So here's the one with just the 4 checks. Rectangle 2, 1, 4, 3 and a point of 1, 3. It's to the left, so they don't collide. Here's a point to the right and below. They don't collide. 0.75. Here's a point inside, so 0.53 is completely within the rectangle, so those two do collide. Here's the rectangle collision right here. So here's the one that's completely to the left and they don't collide. So same rectangle 4, 1, 4, 3, and the second rectangle is 1, 2, 1, 1. Here's 2 rectangles that also collide. 4, 1, 4, 3, 1, 2, 5, 1. Here's the one where the second rectangle completely surrounds the first rectangle, so those two do collide. Here's the last example where the rectangle's to the left and below, so those don't collide. And here's the circle collision. We're checking the distance between the two centers. I don't have the center points on here. But you can see these two don't collide. Circle 2, 3 with a radius of 2 and circle 7, 4 with a radius of 1. They don't collide. But these two do collide. 2, 3 with a radius of 2 and 3, 4 with a radius of 1. Those two do collide because the sum of the radiuses are greater than the distance between the two center points. So I'll put down here the supported collision types right here. But could add lines and circles and lines and rectangles and circles as well. Yeah, so this is basically it right here. It's two files. There's an index.html that basically just has a canvas that this collision demo JS draws on. And I'll also have this checked into GitHub, so I'll provide a link to that as well. So it's pretty simple. I'll just say I have like four classes for each shape type: a point, a line, a rectangle, and a circle. That's just basically holds. These are basically structs. They just basically hold the values. I could add the collision code in here, but I didn't do that. The start gets called when it's loaded up, so it's going to check the parameters. If you specified any parameters within the URL, that's done right here. It gets the parameters using window location search, and then it parses those out using URL search params. Then get all that are defined by OBJ. So if you got two shapes passed in on the command line as parameters, then we're going to get those values, input data 1 and input data 2 by using document get element by ID input data. Actually, yeah, so basically setting those to those two text fields right there. We're getting the values from parse data, then the OBJs is where we loaded those two objects into. So that gives us our data right there, and then set those input values to OBJ S0 and OBJ S1. So if you only have one object defined, then it doesn't display anything. If you define more than two objects, then it's only going to use the first two. So you can either specify the objects through the URL parameters or in those two text fields. So basically in your index.html, whenever you press the button, the check collision button, that's going to call check collision. So check collision basically just loads the two values that are specified in the two text boxes. And it's also important to also set these default to undefined. Otherwise, I think in JavaScript, these are scoped to the whole script and not the function, which I didn't know. I think you can use var or something to scope to the function, but yeah, I learned that out the hard way. I was like, oh, why is object2 defined? And I was like, oh, because it's scoped to the whole script. So we got a draw axis, which is pretty simple right here. It just basically draws way down here. Yeah, draw axis just basically clears out the screen or the canvas, and then draws a red line for the x axis, and then puts the little ticks for the units, then draws an X. Then it draws a green axis for the y-axis, and then draws the ticks, and then draws a Y at the bottom. Nothing special going on there. So basically, this parse data is going to take those two values. Then it's going to run a regex. I've been getting really good with regular expressions lately. So it's going to run a regex for each of the two objects. And so it's going to run one for each object type. So it's going to run a regex on a point, a regex for a line, a regex on a rectangle, and a regex for a circle. And basically, the first letter, so it's basically a letter P for point, L for a line, an R for a rectangle, and a C for a circle. And then an open paren, and then the properties of each of those separated by commas. So here's the regex for a point. It's basically 2 decimal values. I went ahead and put in the extra spaces just in case people put in extra spaces, it still match. Here's the regex for a line. So basically it's 4 decimal values, x, y, width, and height, separated by commas. That's for a line. That's for the line. It's 4 values: x1, y1, x2, y2. And a rectangle is your x and y, and a width and a height, 4 values, and a circle is your 2 decimal values, x and y, and a radius. So if it matches any of those, then it's going to create that new object type, then return that. So yeah, so I got drawing methods for each. I use instance of, so once you got the 2 object classes, and it uses instance of to check what type of object that is, then it draws that line. That's one reason I picked JavaScript, because I knew, so here's like a draw point. I knew JavaScript already had methods defined for drawing on a canvas. So like for a point, I'm using an arc, which is basically a circle. For a line, you use begin path, move to, which moves your, kind of like a, what is it, logo with the turtles. You move 2x, then you do a line to your second x point, then call stroke. Rectangle, there's a stroke rect, call stroke. And a circle, we're using the same arc, specify x, y, and a radius. And that's it for drawing the 4. So that's our draw method right there. So here's the collision. I actually had this appended to the draw. So for each of the object types, then we're going to check if object 1 is a point, and object 2 is a point, then we're going to call collision point point. If it's a point and a line, or a line and a point, then we're going to do collision point line. If they're both lines, then we're going to do collision line line. If we've got a point and a rectangle, or a rectangle and a point, then we're going to call collision point rectangle. We've got 2 rectangles, we're going to call collision rectangle rectangle. I'm following all the same conventions here, and just calling it collision, then the 2 types. We got a circle and a circle, then we're going to call collision circle circle. If we got a point and a circle, we're going to call collision point circle. Or if we got a circle and a point, we could call the same collision point circle. We just flip the 2 objects around if they're backwards. So the collision functions are right here. So this is kind of the same as the C# code, but in JavaScript, checking whether the x and y are equal in collision point point. Collision point line, we're calculating the m, the slope. We're calculating the y-intercept right there. And then we plug in a point. We're just going to use the first point. If it's valid, then it collides. So here we got display collided, so that just displays whether it did or didn't collide. So collision line line. So this is where we're calculating the slope and the y-intercept for both the first and second line. So it's M1, B1, M2, B2. Then we calculate the value of x, which is the x coordinate, where the x value where these 2 lines cross. And then we check to see if the x lies within the minimum and maximum range of both line segments. And if it does, then it collides. Here's collision point rectangle. This is a simple one. We're just checking if the x is within the x values of the rectangle, and the y is within the y values of the rectangle. Here's collision rectangle rectangle. So this is where we test whether the second rectangle is to the left, to the right, above, or below the first rectangle. So if all those don't apply, then it does collide. And here's the collision circle right here. So we calculate our A value, which is the difference between the Y's. The B value is the difference between the two X's, and which is the center points of the two circles. And we use math.pal to get the square root of the sum of the two squares, just using 0.5. So C# automatically handles like the decimals or the real numbers there. In other languages, watch out, because it may convert everything to integers if you're not careful. So then we check to see if our C value is less than the sum of the two radiuses right there. And finally, collision point circle, which requires no additional math. I could have just called collision circle right here and used a circle of radius 0 for the point. But it's the same thing right here. So, okay, so when we check to see if the distance, which is C, is less than or equal, so we're just going. So we only have one point in one circle, so we're just going to check and see if it's less than the radius of the circle, because the point has a radius of 0. And here's where it's displaying collided. So that's basically the script. Yeah, feel free. This is open source, whatever. Use it however you want to. Giving credit is also always nice. But yeah, feel free to use it or update it or whatever. However you want. Yeah, so that's going to wrap it up for Knox Game Design for February 2022. I haven't thought of what next month's presentation will be, but try to get something out there. I know I had to really kind of scramble to get this one done just because February is a shorter month. Still running a little bit late. So anyway, appreciate everyone out there listening and watching. And yeah, as always, we're on Discord. You can go to the knoxgamedesign.org website, and we got links to Discord or the old presentations, and we got Ludum Dare coming up in April, so we may do a small get together in April. I don't know, but yeah, we're still chugging along and get the podcast, which is just the audio on some different platforms. I know some of these platforms aren't working anymore. I think the Spotify and Apple still work, but since these are hosted on a site that isn't using HTTPS, then I think some of these aren't quite working anymore. But you can always listen to the latest one on the website right here, or through the RSS feed. Really hasn't been any new updates to the website or anything else. But yeah, check out the Discord if you want to find out what we're all working on and what we're doing and things like that. So I wasn't sharing that out. Oh well. Anyway, appreciate everybody out there listening and watching, and see everyone back in a month.